In this tutorial, we'll again look at aligning and averaging isolated particles, in this case using real tomographic data. Specifically, we'll use a cryo-electron tomogram of bovine papilloma virus. The sample dataset can be downloaded from the URL shown on your screen. If I open this dataset in 3D Mod, you can see that the individual virions are easily visible and that IMOD model points, shown in green, have been placed at the approximate center of each particle. You'll see that the virions are roughly spherical, which would lead you to suspect icosahedral symmetry, even if you weren't familiar with the known structure of BPV. That suspicion is in fact correct, and we'll verify and make use of this symmetry to improve our reconstruction. Parameters for an initial alignment have been placed in project BindBPV in directory first search, so let's take a look at those settings. We're now using real single tilt axis tomographic data, so I've enabled missing wedge compensation and specified the tilt range in the volume table. I've also specified a spherical mask with inner and outer radii of 10 and 18 voxels to focus on the capsid and suppress noise, neighboring particles, and nucleoprotein. We'll see shortly how to verify that the mask is appropriately sized and centered on the reference. Scrolling down to the bottom of the Setup tab, you can see that I've also selected Uniform Random Rotations for the initial motive list. Since we'll be using a limited range angular search, this randomization will minimize alignment and reinforcement of missing wedge artifacts. Moving on to the Run tab, you see that except at the first iteration, the iteration table follows the 3-to-1 pattern recommended in the previous tutorial. At the first iteration, I've specified a 4-to-1 ratio to provide a broader range initial search. The first search covers a 72-degree range for each particle. Recall that an icosahedron has a number of 5-fold rotational symmetry axes, which suggest a 72-degree search range should suffice. Additionally, the distance between neighboring 5-fold axes is also less than 72 degrees. It's because of this limited search range that randomization of the starting orientations helps suppress missing wedge artifacts. If a full spherical search was used, that option, while harmless, would not improve the results. These data are binned and relatively low noise, so I've chosen a high-frequency cutoff of 0.3, which represents mild to moderate low-pass filtering. On noisier cryotomograms, a cutoff of 0.1 would not be unusual. Finally, I've selected a reference threshold of 350, or about 2/3 of the total number of available particles at each iteration. I've already run an alignment using these settings, so we can skip that step and proceed to examining the results. First, if I open the references from the various iterations and adjust the contrast, you can see that the mask, while not perfectly centered, will suffice to restrict alignment to the capsid. If I open the averages, you'll see that they don't change greatly with the number of particles averaged, and that the capsid proteins are easily seen. Notice that we can easily identify pentamers, each of which locates a pole where a 5-fold rotational symmetry axis enters or leaves the volume. If I rotate the isosurface view of the average, you'll see that it's nearly isotropic, without apparent missing wedge artifacts. For comparison, I've also done a reconstruction without randomizing the starting orientation. In that case, you can see that the average is no longer isotropic, with higher resolution in one direction and increased smearing in an orthogonal direction due to the missing tomographic wedge. Often, you'd like an estimate of the resolution achieved in the average. PEET provides programs CalcSSNR and CalcFSC to compute spectral signal-to-noise ratios and Fourier shell correlations, respectively. There are, of course, man pages describing each. In this case, I'll run CalcFSC to compute the Fourier shell correlation, and then after waiting for it to complete, we'll run PlotFSC to display the results. You'll see that we currently have a resolution of about 5 nanometers at the 50% response point. Consult the man pages for other options, including plotting error bars or plotting against spatial frequency rather than resolution. Our initial reconstruction is good enough to verify the assumption of icosahedral symmetry, so let's see how to exploit that symmetry to generate a more accurate, higher resolution average. An icosahedron contains 12 pentamers at the poles of 5-fold symmetry axes. We'd like to identify those points and the angles required to position them in some standard orientation. Here I've opened up linked isosurface and slicer views of the average from the previous run. I've located and placed an iMod model point at the center of each pentamer. I'll turn down the isosurface threshold to make these model points more apparent, while still leaving most of the capsomers visible. Here you can see that I've rotated the average to one such standard orientation where there's a pentamer at the North Pole with one of its vertices at approximately 6 o'clock. You can see 10 of the other pentamers around the periphery. The 12th is at the South Pole, so we're looking directly down along a 5-fold symmetry axis. I can make the remaining pentamer visible either by scrolling down in the slicer window to the bottom of the virus, or by tipping the isosurface view slightly so the symmetry axis is no longer vertical. What we need to do is record the slicer angles required to bring each of the 12 pentamers to this or some other standard orientation. One convenient way to do this is to add iMod model points to opposing pairs of pentamers as you find them, rotate to the standard orientation, and then use iMod's Edit Angles Save functionality to record the angles in the model. Now we'll use this information to generate a symmetrized average in the directory named 60x icosahedral symmetry. Note that in our initial search we ran 4 alignment iterations, so the motive list reflecting that alignment is in the file with the suffix iter5.csv. We'll use this file as input to program modify motive list to generate initial motive list expressing the various symmetry operations. I've created a shell script named reorient.sh to do these operations. First, modify motive list is invoked 12 times using one of the saved sets of slicer angles each time. This generates motive list v1.csv through v12.csv, each of which will position a particular pentamer at the North Pole in the chosen standard orientation. Since v1 through v12 each position a 5-fold axis along the z-axis, we can then run modify motive list 4 more times for each to generate motive lists with suffixes a through d, each rotated an additional 72 degrees around z. This script takes just a few minutes to run and generates a total of 60 initial motive lists. Project settings to make use of these initial motive lists have been placed in project bin-to-bpv in the 60x icosahedral symmetry directory. I've selected user-supplied initial motive lists and have modified the volume table accordingly. Instead of a single line, we now have 60 volumes specified, each pointing to our original tomogram and model, and each associated with one of the newly created motive lists. Here you see the entries for the first pentamer, which I've called V1. If I scroll down, you see the entries for the final 12th pentamer. On the Run tab, I've also changed the iteration table accordingly. The first iteration now does no search at all, but simply generates a new symmetrized reference based on our initial motive lists. Then, an abbreviated 2-iteration alignment search is conducted to compensate for the fact that both the initial alignment and the symmetry operations are imperfect estimates. To prevent bias arising from multiple references to the same particle, I've also selected the option to remove duplicate particles after each iteration. Here, I've chosen parameters which say that particles will be considered duplicates if they have the same orientation within 1 degree and the same position within 1 voxel. Because we now have effectively 60 times more particles, I've raised the reference thresholds and the number of particles to be averaged accordingly. Finally, I've also raised the number of particles per CPU from the default of 5 to 20, simply to reduce the number of chunks run and the number of log files created. The resulting averages are now essentially isotropic and free of missing wedge artifacts. The Fourier shell correlation indicates a resolution approaching the Nyquist limit. For purposes of this tutorial, however, these data have been binned down 2-fold in each dimension, so the real resolution is not particularly high. Additionally, these data were acquired with a rather high defocus of 8 micrometers. That also improves contrast and visibility, but impairs resolution. As an example of what PEET is capable of, I've created averages from a threefold smaller unbinned dataset collected at 3 microns under focus. Results in this case indicate a resolution at 50% response of between 3 and 3.5 nanometers and in good agreement with the known structure of BPV. So now you've seen how to align and average single particles while compensating for a single tilt-axis missing tomographic wedge, and how to identify and exploit symmetry when present to improve your results. In the following tutorial, we'll explore some of these same issues for the case of subunits that repeat along a filament axis.